Hello and welcome. My name is Max, and in this video I will present the demonstrator system that has been developed at the Chair of Integrated Systems at the Technical University of Munich in the scope of the Aramis2 research project. The demonstrator consists of two parts: a mixed-critical tiled 3x3 system which is based on OpTiMSoC and implemented on an FPGA, and a host PC that runs the demonstrator control panel and a monitor UI which shows the network on chip that is used by the system. The system has 8 compute tiles, which each contain an OpenRISC core, a local memory, and a network adapter to connect the tile to the NoC. The system uses a hybrid NoC that supports two types of traffic: packet switching and time division multiplexing. In a demonstrator, packet switching is used for best effort traffic, and time division multiplexing is used for critical traffic, where latency and throughput guarantees must be given. To demonstrate a mixed critical system with different clock domains, we selected 3 of the compute tiles as critical tiles. These tiles are clocked at 100 MHz and run a pedestrian detection algorithm. The host PC sends frames for processing to the critical tiles via the I/O tile and the network on chip, waits for the result, and then sends the next frame. The remaining 5 compute tiles are clocked at 50 MHz and run an application that produces and consumes uniform random best effort traffic as background traffic. The network on chip is currently clocked at 20 MHz. Protection switching is used to make the critical communication fault tolerant. To achieve that, each FLIT is sent twice over 2 disjoint paths, so if a fault occurs on one of the paths, the FLIT will still be delivered on the other path. The purpose of this demonstrator system is to demonstrate both the fault tolerance of the critical communication as well as the traffic isolation between the best effort and the critical traffic. First, we must program the bit stream on the FPGA. This typically takes some time, so I sped up the process here a bit. Now we can start the host application, which will connect to the FPGA, show a control panel for the demonstrator, and start a local server which we can connect to with a browser to show the monitor UI. The control panel shows us 3 critical cores in tiles 1, 2, and 7. In the monitor UI, we can also select the uncritical tiles and configure what other tiles they should send best effort traffic to, or define burst sizes or delay between 2 bursts. The I/O tile is used for the communication with the host PC. Before we can start, we must load the target application into the local memory of each tile. You can see the progress in the terminal in the background. Now we must train the pedestrian detection algorithm for the image classification. In this example, we send a pre-trained data set to the cores. As this is done, you can see a small spike in the TDM utilization on the right. When we start the pedestrian detection, we can see the utilization of the individual links visualized in the monitor UI. However, as you can see in the diagram on the right, the overall utilization of critical traffic is relatively low in this example. The monitor UI also allows to select and inspect individual links. When selecting a link, the utilization of this link is shown in the diagrams for best effort and critical traffic. We can also see the reserved slots for critical traffic. Furthermore, it is possible to inject faults on a link. To demonstrate the protection switching, I inject a fault on the link from router 3 to router 4. As can be seen, the processed frames per second are totally unaffected, showing that the communication with all critical cores is still possible. If I inject a second fault on the alternative path to tile 2, we can see that the communication is broken and the tile no longer processes any frames. The same happens if I inject a second fault on the alternative path to tile 1. When the first fault is removed, communication with all the critical tiles is possible again, and the processing frame rate goes back to where it was before the faults were injected. To demonstrate the traffic isolation, we generate best effort traffic as background traffic. It should be noted that the monitor UI not only considers a link to be utilized when a FLIT traverses the link, but also when a router wants to send a FLIT but cannot do so because of back pressure. For this demonstration, I create back pressure on the link from router 3 to router 0. To do this, I deactivate all outgoing traffic from tile 0 and select tile 0 as the only destination for all the other non-critical tiles. Even with just 2 tiles only sending packets to tile 0, we can already see a large increase in the utilization of the link. With 4 tiles only sending packets to tile 0, we can see that the utilization of best effort traffic on that link almost reaches 100%. The utilization by the critical traffic is relatively low but completely unaffected by the best effort traffic. When we deactivate the critical traffic, we can see that the best effort utilization on that link reaches 100%. However, as soon as we reactivate the critical traffic, we can see that the critical traffic gets all the bandwidth it needs, demonstrating the traffic isolation. When we go back to uniform random best effort traffic, we can see that the link utilization goes down to normal and the back pressure is resolved. This brings me to the end of my presentation. I hope you enjoyed it. Thank you for watching and have a nice day.